So factors that increase the reaction rate. Increasing the reaction concentration will increase the reaction rate in most cases. Increasing the reaction temperature. In general, you can double the rate of chemical reaction by increasing the temperature by 10 degrees Celsius. So by heating things up, you can make things go a lot faster. Or by adding a catalyst. You reduce the activation energy, and then the chemical reaction happens a lot faster. For the reaction of carbon dioxide with water, predict which set of conditions will yield a faster reaction. Well, here we have carbon dioxide is 100 torr versus 150 torr. Same temperature, same activation energy. We're going to expect condition 2 to react faster because you have a lot more carbon dioxide present, because the gas is at a higher pressure, which means there's more molecules per any given volume, which means greater concentration. Here, in 2, notice the activation energy is lower. That'll make things go a lot faster. Lowering the activation energy with a catalyst is an absolutely good way to make a reaction move a lot faster. Michaelis-Menten plot. The rate of an enzyme-catalyzed reaction is a function of the substrate. And so here we see your fastest reaction always occurs at the very beginning. And then as you keep adding more and more substrate, the reaction starts slowing down until you hit your maximum velocity. Notice on this y-axis is a velocity, the speed. And so the change of the speed, or the acceleration of the reaction, is that first derivative. And so we notice at the very beginning, as we add more substrate, the reaction increases its rate pretty rapidly. Because there's just enzymes hanging around doing nothing, so as you add more substrate, they jump in and start working really fast. By the time we get over here, all the enzymes are pretty much working already, and they don't really have much downtime. So as you keep adding substrate, you don't really get much more reaction rate, just because the enzymes are pretty much reaching their maximum saturated speed. Like, imagine if you have a garage with 10 mechanics and you have one car to work on. That work is happening on that car really fast. Let's say you put another car in there. That still happens pretty fast. We put a fourth and a fifth car in there, and now it's going to start. It's still going fast, but it's not as fast as it used to be in each car, because each mechanic is having more and more work to do. Once we get to 10 cars, we've hit our maximum speed. Every mechanic has a car they're responsible with. And so now as we keep piling cars up, the rate doesn't go up any faster. We've hit maximum speed that they can fix cars at, and just by bringing in more cars doesn't mean anything is going to happen faster. So at the beginning, things only happen faster because there may be 3 mechanics working on that first car, and there were 7 mechanics drinking coffee waiting for some work. And so as soon as the second car came, they all jumped at it, and so now there was more work happening in that garage. And so enzymes are similar, that you can saturate them. And once you saturate them, you hit the maximum velocity possible. And here we see the Michaelis-Menten plot for 2 glucose metabolic enzymes, hexokinase and glucokinase. Hexokinase is a stronger attraction for glucose than glucokinase, and the reaction is a lot faster. Turnover number. This is used to measure catalytic speed, the number of molecules that the enzyme can convert or turn over in a given time span. And an enzyme's catalytic speed is matched to an organism's metabolic needs. A convenient way to compare enzymes is to determine the effect of reaction conditions. So the enzyme lactase can break down 1,197 molecules of lactose in 7 minutes. Give the turnover number per minute. Well, molecules divided by minutes, 171 molecules are being turned over per minute. Not only are enzymes important in biology, but they are increasingly important in industry. About 75% of industrial enzymes have a digestive or a breakdown functions. They are hydrolases, but are known by their common names. So the proteases, these break down proteins and chop up peptide bonds. Lipases, these digest lipids. And the cellulases, amylases, xylenases, lactases, and pectinases, these break down those molecules respectively. Cellulose, that's used in the juice industry. If you break down all the cellulose and you squeeze a fruit or a vegetable, you get a lot more juice out of it. You can break down lactose to have lactose-free milk. Well, we break down pectin in plants for a lot of different products. Enzymes used in food processing. Amylases and other carbohydrate hydrolases act to soften dough by breaking down those bonds. About 25% of all industrial enzymes are used to convert cornstarch into syrups. Because cornstarch, like with any starch, is a long chain of glucose. And if you chop them up into much shorter chains, now you have a syrup, a sugary solution. The plant products used in animal feed are also commonly treated with industrial enzymes to make them more nutritious. And industrial enzymes offer solutions to environmental pollutions. So a number of industries use cellulases instead of strong bases to give a soft appearance to denim. And so jeans are actually treated with these enzymes to fade them because people like how it looks. Enzymes used in detergents. There's proteases that digest stains like grass and blood and sweat. And about 37% of all industrial enzymes are found in laundry detergents to help clean things by chemically destroying them. Lipases hydrolyze fats, amylases digest starch. And enzymes are used in medicine. Several proteases are used to dissolve blood clots in patients with lung diseases, such as an embolism, which is a clot in the lung, or a stroke, which is a clot in the brain, or a heart attack, which is a clot in the cardiac arteries, which are feeding the heart oxygenated blood. Explain why cellulases are not used to soften nylon fabrics, because nylon does not contain cellulose. Nylon is actually a completely man-made polyamide and therefore would not react with cellulase.